Hello, everyone. Thank you for watching. I'm Paul Pen from Tech. This video, let's prove theorem 1.4, the Cauchy-Schwarz inequality. That's a super famous one. Okay, very good result. It says this. It says the dot product is no. It's controlled by the product of the length of two vectors in general n space. It's not only two space or three space. Okay, Euclidean space. And this theorem, this inequality exactly is the foundation that we can define angle in general n space. Okay, we can extend the Euclidean geometry into high dimension space. So this is really a foundation because see, so u dot v divided by the length, and then you will see the left divided by the right will be between -1 to 1, okay, which is exactly cosine theta. Cosine theta is between -1 to 1, so therefore we can exactly define what is the angle between two vectors in general n space. Okay, super good. I introduce a proof for this. Let's see how we can prove it. And also the proof is super good. Okay, as you can see, that's a very popular one from the history. Okay, long time ago. Let's start it from this in space. Okay, as a look at it. This one is this less than the question? It says this less than here. So our purpose is to see that we can have 4 on both sides. Okay, and this is exactly equals equivalent to if I times 4. Let's square it. You will see very strange. Okay, a square the left, a square the right, they are the same. And then times 4. Okay. Times 4. So therefore, do you believe is the same as 2? Okay. So let me do. It's okay. Times 4. Okay. So u dot v. So these are my absolute value. I can take it away. Okay. Now this is squared. They are the same. Okay. Of course, we think about it. So why this is correct? Then have you seen something? So like a b squared minus 4 ab. What is b squared? No, b squared minus 4 ac. Somewhat like a discriminant of a quadratic function. Okay, so we would do that. That's really fancy. Okay, so you can see. So we would do that. Which minus 4 minus 4. Do I have to put this inside? So where we put so b squared 4 ac. Okay. Where the 4 we put? I don't know. So let's put, okay, so which is a 2 u dot v. And you see it's the same, right? Minus 4. So this is number a. Okay, so I have to put here. Wow, they are the same. Okay, and this number definitely is similar. Like okay, this is so b squared. If that b squared minus 4ac. Okay, b squared minus 4ac, which is there. Okay. And this is less than 0. Okay, what is b? So therefore, we put a b. B will be 2u, right? A will be and then C will be okay. So now we set up. Is that true? So this is similar like is that less than 0? So means the quadratic. Okay, so let's make a quadratic function. Okay, which is a b ax squared plus. Okay, so then let's see, which is a is that. So a, right, x squared plus bx. What is b? B is 2 u dot v. This is a number, okay, whatever, x. Let's see. Yeah, you see, for quadratic, this is a quadratic function. So x are real numbers. The coefficient definitely real numbers. Okay, so this is a quadratic function. Is this a quadratic function? Should it be open up because the coefficient is positive? Open up because the discriminant is negative. Okay, which means we don't have a negative solution, right? We don't have a negative value, which means this has to be always greater than or equal 0. Is that true? See, that's a quadratic function. Similar like so this one will be ax squared plus bx plus c. This function, right? So probably you can say fx equals that quadratic function has to be greater than equal 0. Okay, for all x are real numbers because the delta equals b squared minus 4ac, see, less than 0. So this number is super good. Okay, now we have to see, is this true? And for all x, okay. That's a big one. And this is true for all x. Real number. Let me just highlight. So the original question we want to see from the beginning is the same as we have to prove these quadratic function and because they open up. Okay, so always someone add this. This is kind of see, right? So because the delta is less than or equal 0, okay, so the function should be up. Probably touch x-axis, doesn't matter, okay. So is this true? Which means the y value of the function is always positive or non-negative. That's all we need to do, right? Is this true? Now we just do manipulation, okay, a little bit. So look at the f. This is f, right? This is fx. Let's see. We check. So this fx equals. I can do a little bit. Okay, can you see? We can do that times x, right? The first term. The second term, what do I do? U and x are together. Okay, probably you can put, how I can say, put 2, right? and then x is a number times u, right? That's a vector, and then dot v. Oh, the same, okay. And then the third, let me just put, this is a, have you seen something? This look like a perfect square, okay. It's a really perfect square. A squared plus 2AO, but that's not 2AB plus B squared. It is, okay. Do you believe it is? Oh, I can say, so these x, I can put x inside, okay. You see, if I do this, you will see it even more clear. Okay, so I can get something like xu, and then v. Do you believe this is a perfect square formula? Perfect square, okay, something like a perfect square formula. So therefore, this plus that a little bit different. A little bit different. So you can think, but it is true. Okay, it is true. I can do, because it is squared, which means xu dot dot xu, you can see, right? And now plus 2 times xu dot v. Okay, you are familiar, it is. And then it's v dot v. Have you see? So we definitely have a two, okay, two vector. This is a one vector. So another is v is a vector. And the xu dot v will be the crosstalk, the intersection. So therefore, this is a perfect square, okay? It's what? It's xu, let me see, it's xu plus v, and then dot xu plus v. Can you see? And so after you distribute the first, the last, the middle term, okay, it's just a double, which is what? Okay, which is quadratic. So this is the length of xu plus v, and the square, perfect, okay, so perfect, this is greater than or equal 0, and it's true. Have you see? And now is the proof. The last one, this quadratic is always, you can think about it backwards, okay? If this quadratic function is all, no, this quadratic function is all so non-negative. Non-negative, which means the discriminant has to be less than 0. Discriminant is that, okay? You get back, okay, to simplify, we definitely get the Cauchy-Schwarz. Yeah, that's all. Thank you.